All right, so welcome everyone to the Alaska Science Training for Tour Guides workshop, which is hosted by Explore Fairbanks and Alaska EPSCoR. So I want to give a quick introduction of Alaska EPSCoR, and also real quickly, I'd just like to ask everybody if you can have your mute on, that would be great. And that way we don't have any interruptions. So if everybody who's just listening in kind of quickly mute yourself. So a quick introduction of Alaska EPSCoR. Alaska EPSCoR is supported through the National Science Foundation and state funds. And we work to improve Alaska's scientific capacity by engaging in research projects. And our current project is termed Fire and Ice, and it studies climate-driven changes to Alaska wildfire regimes and coastal ecosystems. So now I would like to introduce Scott McCree from Explore Fairbanks. He's just going to say a few words, and then we will move into starting presentations.
All right, great. Well, yeah, thank you, Tara. And yeah, a big thank you to EPSCoR and this outstanding panelists that we have here today. I'm Scott McCree, Director of Tourism, Explore Fairbanks. Hello to the Explore Fairbanks partners who are on board today. So we had this partnership, I think we last did this back in 2017, in which feels like an entirely different world because we did this in person. We all got in a classroom, and EPSCoR provided another great group of panelists to help give some good information to local guides about the science of Alaska, the topics that we're seeing today. And we knew early on this year we wanted to do something else, and then of course the world kind of changed on us a little bit. And like so many things that are being done today, we're using the webinar, Zoom platform. But looking forward to today's presentations. I know some of our partners had questions about, and as Tara mentioned, this will be recorded, so we'll be able to send it out after the fact. I know some of you on board, you might not have your guides on board yet. You're looking at a later summer dates. So we will send the link out with partner e-news, so you've got that available to share with your staff as need be. And with that, I will turn it back over to Tara. Thank you again.
Thanks, Scott. And real quickly, I just want to introduce Tom Moran, who's also on this call. He's our communications manager at Alaska EPSCoR, and he's going to be helping with fielding questions throughout this webinar. And so with questions, we're going to have time at the end of each presentation for any questions you may have, and we'll have two ways you can go about asking a question. There is the little button where you can press where you can raise your hand, and if your hand's raised, we can call on you and unmute you and you can ask your question directly, or you could put your question in the chat box. And if you're using the chat box option, you can throw your question in there during the presentation and we'll come back to it after. But I just want to make a quick note that we have limited time because we have a lot of presentations, a lot of good content to go through, so we might not be able to address all the questions. But with that, I'd like to give a quick introduction of each speaker. So we have 5 speakers today. First, we're going to start with Rick Thoman, and he is an Alaska climate specialist with the Alaska Center of Climate Assessment and Policy at UAF, and he's an expert on Alaska's weather and climate. Next, we'll have Jessica Garron, a senior science consultant with the Alaska Satellite Facility at UAF, and she has a background in ecology and soils research. Todd Brinkman is not able to be with us today. He had to go out in the field. He'll explain this a little in his pre-recorded presentation. But Todd is an associate professor of wildlife biology at UAF and the Institute of Arctic Biology, who focuses on human dimensions of wildlife science. Next, we'll have Alison York. She's the coordinator of the UAF-based Alaska Fire Science Consortium, an interagency group that coordinates fire research and connects researchers and fire managers. And finally, we'll have Mark Conde, a professor of physics at UAF, who specializes in the aurora and space weather events. So with that, I would like to get started into our first presentation from Rick. So I will begin sharing my screen, and Rick, have at it.
Hi, hi everyone. Can you hear me?
Yes.
Okay, great. Well, thank you very much, Tara and Tom for the invite here. And so I'm going to talk a little bit about weather and climate. Obviously, I could talk for a lot longer than 15 minutes about this, and you probably could too. But we'll just do a little taster here, and then can always follow up. So, as Tara said, I work for the Alaska Center for Climate Assessment and Policy, a NOAA-funded group, and we're housed within the International Arctic Research Center in UAF. And this is kind of my Walmart greeter retirement job. I spent 30 years with the Weather Service in Alaska. So next up.
Okay.
So next slide, there we go. Okay, so I'm gonna talk to folks about Alaska weather and climate. It's definitely a good idea to be clear on the difference between weather and climate. Sometimes people inadvertently or on purpose interchange those, but they're not, of course, the same. In the strictest sense, weather is kind of the instantaneous state of the atmosphere. So what's the temperature right now? What's the precipitation right now? What's the sky cover, cloudiness right now? A weather forecast might include things like, it's sunny currently, but do I need to take an umbrella? When we get to climate, climate in the end is nothing more than the statistics of weather. So if we can make a statistic out of it, that from the weather, that falls into climate. So something like today's high temperature, we actually think of that as something to do with the weather. Actually, it's a statistic, right? It's the highest value from many individual readings of temperatures today. We don't usually use it like that, climate. We typically think of referring to at least weeks and for weather or climate outlooks, and slides are going nuts. Often when we think of climate, we think of some long-term, decadal scale reference to baseline. Depends on the purpose, though. We usually use decades, but the geologists might think of climate in terms of millions of years kind of thing. So you may have seen some of these quips in red here. So climate's what you expect, weather's what you get. Folks come to Fairbanks in January, they might expect it to be 20 below, but it might be 50 below, and it might be 30 above. Weather's what you wear today. Do I need to wear my parka today? Or, but climate is what's in your closet. And if you're a sports fan, you might like the Babe Ruth analogy. You may have heard of this guy, Babe Ruth, said to be a great home run hitter. And he was over the course of the career, but the weather part of Babe's career was the individual games. And of course, not every game did Babe hit a home run. The climate is the individual games are the weather, long-term versus short-term. Okay, next slide. All right, you all know from your experience, Alaska is a land of extremes. If you get asked what's the climate here? Well, it turns out that nearly all of mainland Alaska falls into a subarctic climate. The areas that get qualified as polar or Arctic tundra are actually fairly restricted to the North Slope coast and a little ways inland, as well as places like the Bering Strait coast, St. Lawrence Island. But that's almost the only polar tundra. Southeast Alaska falls into the temperate climate classifications. And then, of course, mountains, because they are so diverse, they have their own kind of ill-defined highlands climate. Now, this is, we tend to think of these kind of broad classifications as static, and but they're actually changing. For instance, in South Central, places are threatening. They have or will soon move from an subarctic maritime climate to a temperate climate because temperatures are warming enough now in the fall that September will soon have an average temperature above 50 degrees, and that will give them 4 months with averages above 50, and that's a commonly used separator between subarctic and temperate climates, how many warm months or mild months a year you have. So while we tend to think of this as static, it really is actually changing noticeably across the state. Next slide. So for Fairbanks and the interior Alaska, maybe you kind of thought this intuitively, but if you count the 90 days of the year that the average temperature is highest, it is now summer in Alaska. In interior Alaska, we actually start our warmest 90-day periods, interior Alaska eastward into the Yukon, earlier than anywhere else in North America. And that's a combination of our latitude, where we're very, even as the sun gets lower in the sky in August, it starts to cool off very noticeably, and our very continental climate in the interior, protected from the ocean by the big mountains, even though we're not that far as the raven flies from the ocean. There's no community in Alaska is more than 300 miles from salt water, and yet we have an extremely continental climate here in the interior. And so we start and end our summer earlier than any other place in North America. That's of course quite different along the coast, where the ocean and or sea ice influence is much greater. And as you can see, it's not just a function of latitude. Even on the North Slope, summer comes and goes, comes weeks later than in the interior, and really extreme in the far west and southwest. Next slide. All right. For those of you that live in Fairbanks, you know we are at the heart of Alaska's thunderstorm region. This is a plot of basically the frequency of lightning as detected by the Alaska Fire Service's BLM's lightning detection network over more than 25 years there. And you can see that basically the Yukon-Tanana uplands to the east and northeast of Fairbanks are the center of thunder activity, but fairly high frequency across most of the interior, dramatically less, of course, south of the Alaska Range crest, although there is another small peak kind of in the Talkeetna Mountains there. Lightning does occur on occasion, almost everywhere, of course, although in places like southeast, their peak thunderstorm season is actually in the autumn, associated with weather fronts as the atmosphere is cooling, but oceans are at their warmest at that point. So then even in the Fairbanks area, if you look close at this graphic, you can see that over the uplands to the north and east of town, the frequency of lightning strikes is more than double what it is out on the flats south of town. That probably comports with your experience as well. Next slide. All right. Summertime in Alaska. Here in the interior, this is easily our wettest season of the year. That is the most precipitation. And as you can see, kind of the darkest green colors are areas that get more than half of the annual precipitation falls in the 3-month summer. And you can see basically Fairbanks eastward falls into that, as well as parts of the North Slope. And nearly all of the interior, except for the far west, gets more than 40% of the annual precipitation this time of year. Not hard to guess why that would be the case. The atmosphere is warmest in the summer. The warmer the atmosphere, the more water vapor the atmosphere can hold. And so we take maximum advantage of that. Less so along the coast, Anchorage, Southwest, and the Panhandle especially are much more autumn-dominated rain areas. Nearly all of Alaska, of course, does have a very strong seasonality to precipitation, in spite of this April, which was quite wet. Typically, springs are very dry in interior Alaska. Almost the only place that has kind of a close to even distribution of precipitation through the year is actually Kodiak Island. Even in Southeast, there is something, comparatively speaking, comparative dry season during the late spring and early summer. Next slide. I just thought I'd throw in these factoids. I'm sure that some of you will get asked these. I won't bother to read them, but you can print them out and stick them in your pocket. And so when someone asks you, well, how hot does it get in Fairbanks? You'll have the answer right there. And again, as for those of you that live in Fairbanks, you know that, you know, people think, oh, you know, big snowstorms, that's your big problem, or deep cold. In fact, of course, the highest impact weather that we have had historically in Fairbanks is flooding, and some big flood years there listed. Of course, in the early days, the Chena breakup on the Chena would rip out the bridge every spring. Those days are long gone. But of course, the flooding in the 30s, 40s, into the 50s and 60s, of course, eventually prompted the construction of the Moose Creek Dam, which is not, of course, most of you know, is not a dam per se, in that it's always impounding water. It's a flood control project. We would have had flooding this spring in urban Fairbanks had it not been for the impounding of water there this spring. First time, I think, since 2002 that flood control project was operated during spring breakup, and as a result of the high snowpack in the upper Chena Basin. Next slide. Same idea here, just some Alaska weather trivia, again, print it out, put it in your pocket. Some of you will immediately jump up and down and say, oh, but there's a sign at Coldfoot that says it's 83 below there in 1989. And it may have been 83 below in Coldfoot in 1989, but a thermometer hanging on the porch at Coldfoot Services does not count. These are Weather Service, Weather Bureau sanctioned observations. No one doubts that it could be colder than 80 below somewhere in Alaska, but we just don't have very many observations. We only have the Prospect Creek one because they only took observations for a few years during the pipeline era, and it happened to be the January 1971 is one of the historically great cold snaps there. 100 degrees at Fort Yukon there's been arguments in the climate community about it, but my opinion is it's probably accurate. At any rate, if this is useful to you to answer folks' questions, there you go, you got it. Now, this is kind of the part you're surely going to get asked about climate change. And so I just want to set the stage for that. Alaska, what controls our climate? Well, the first and biggest control is that we're at high latitude. Of course, 85% of Alaska land area is north of 60 degrees latitude. A quarter of Alaska is north of the Arctic Circle. And that means there's a huge difference in solar heating, summer to winter. For comparison, the difference between June solar heating and December solar heating at 40 degrees north, so roughly the latitude of Philadelphia or Kansas City or San Francisco, it's about a factor of 4. In most of mainland Alaska, of course, it's a factor of hundreds because there's effectively no, or there is no north of the Arctic Circle, heating during the winter. So it's that big seasonal difference that makes is a big control. The other one is we live in a land of complex terrain. Mountains modify everything. Can't really overemphasize that. That, of course, is not unique to Alaska. Mountains modify everything in Colorado and Wyoming as well. And as I mentioned or alluded to, Alaska is one big peninsula. Did you know 25% of Alaska land is within 20 miles of salt water? When I learned that, I actually asked one of my GIS friends, can you confirm this? That can't be right. And yes, it is right. And as I mentioned, every community in Alaska is within 300 miles of salt water. Eagle is the winner for farthest, and they are at 300 miles. So those, of course, are things that are fixed on our time scales. There are things, though, that are changing, and some of them are changing in a hurry. Fastest changing things are the frozen parts of our environment. Sea ice, river ice, snow cover, permafrost. It's not just overall changes, but changes in seasonality as well. And of course, vegetation is also responding that, as are animals. Those kind of things respond at slower time scales. But we see now that Alaska, interior Alaska, especially eastern interior Alaska, is getting too warm to support things like white spruce, whereas southwest Alaska is getting better for white spruce. Next slide. All right. Why is Alaska's climate warming? And it's warming much more than the lower 48. Graphic on the right shows the total temperature change in degrees Celsius in the last 60 years. And you can see the red bullseye right over the North Pole, northern half of Alaska warming very substantially, but all of Alaska warm faster than most of the lower 48. And that is mostly tied to decreases and thinning of sea ice, shorter snow cover season. And another important factor is, of course, as the atmosphere warms, it can hold more water vapor. Water vapor is in itself a significant greenhouse gas and supports clouds. Next slide. Temperatures are going up. This is from the well-known NASA database here. Average temperature, this is for the state, since 1900. And the way I like to do these, the blue dots are the 10 coldest. The red dots are the 10 warmest for our 120 years here. And you can see that 5 of the warmest 10 years in the past 120 years have occurred since 2013 in Alaska. And there's only a couple years there prior to the 1990s. On the other hand, there hasn't been a top 10 coldest year since the mid-1970s, and there's really nothing even close. Next slide. Regional distribution over the past 50 years. Here's the total changes that we've seen. There's nothing magical about 50 years. I picked that because that's kind of the working adult memory. Some of us remember 1970. Not many of us remember 1920. The warming on the left-hand side is not evenly spread across Alaska. Biggest changes are in the north and west. That's due principally to changes in declines in sea ice, both the thickness and the seasonality, and also due to warming ocean temperatures as well. Precipitation on
Amy, you're not listening to these EPSCoR. Is anybody from your team listening to this stuff? The EPSCoR thing?
Hello?
I muted them. Go on, Rick.
Okay, sorry about that. Precipitation on the right-hand side is much more variable than temperature. It's much harder to analyze on the regional level. But as you can see here in this graphic, over the last 50 years, precipitation is trending up at the annual basis. Although some areas it's really kind of a wash. It's the 3% per year in the Cook Inlet region there. That's not really significant. On the other hand, southeast interior, where Fairbanks is, of course, is significantly wetter now than 50 years ago. So that it's interesting to see, but it's not nearly as firm as the temperature trend. Next slide. Spring breakup. Of course, many of you have seen some version of this graphic. Maybe you've made one yourself to put money down on the Nenana Ice Classic. I like this particular version that I made up. It's just the dates here since 1917. And the green band here, that's kind of the near normal band. And what's really interesting, and from the climate science perspective, is really telling. You can see that where we're at now on the left-hand side of the plot, the green band goes up to about May 1st. Well, if you scan over to the left, you can see that prior to World War II, and really through most of the 20th century before the 80s, May 1st would have been an unusually early date, not record early, but it's pretty clear that we have quite a dramatic change. Tanana River breakup at Nenana is fairly tightly confined, typically a week either side of the average, and we have changed by about a week. So that is, even though it doesn't sound like a lot, it's actually quite a dramatic change for something so tightly constrained. Next slide. And just a couple of plugs here. We'll hear more about this coming up here in presentations in just a few moments. You all know the frequency of wildfires is increasing in Alaska. This is just a plot of the annual acreage. The red bars are years with more than 1 million acres, and the frequency of those 1 million acre seasons has doubled since about 1990 compared to before that. And my last slide, I think. Permafrost changes, we'll hear more about that. These are just some pictures from around Fairbanks, whether it's improper construction or problems on roads, or our own version of sinkholes. Thawing permafrost is a big problem, and in the long run, thawing permafrost, because it impacts expensive infrastructure like buildings, like utilities, like roads, will wind up being an extremely expensive aspect of climate change for Alaska. And with that, I will stop.
Thanks, Rick. That was awesome. Now we would like to take any questions. Tom, did you receive any questions in the chat box?
I did not, in fact, so we can open it up to the floor.
Okay, so if anybody has a question, I think there's a raise your hand mode. You can raise your hand, or you can throw it into the chat box. Any questions?
Here's your chance.
Yeah. Not seeing.
I'll ask one.
Okay, go, Tom.
Let's jump on in. I'm just curious, maybe you said this in it, but can you explain the geographic distribution of lightning around Fairbanks? Why there's more in the hills than in the flats?
Okay, so why is there more lightning in the hills than on the flats? Great question. Well, the answer is, it turns out, unlike, say, Kansas, we almost never have thunderstorms that form because of things like weather fronts. They're almost entirely just the result of heating of the ground. At our high latitude, the middle levels of the atmosphere are almost always pretty cold. And so the elevated terrain of the uplands serves as basically the being able to get that heated air starting out higher. And so it bubbles up. And actually, a lot of that lightning over the flats winds up being from storms that form over the higher terrain and drift out that way. Doesn't always work that way, but it's if you compare that lightning distribution to, say, a topographic map with elevation, the match would actually be surprisingly high.
Okay, thank you.
Any other questions before we go on to our next presentation? All right, not seeing any. Thank you so much, Rick. That was fantastic.
You bet, thank you.
All right, so our next speaker is Jessica. So I will go to screen sharing and start your presentation.
Great. And while we're getting the slides queued up, just a few things about me. I actually have moved on from the satellite facility, and I'm now the science team lead for the Alaska Center for Unmanned Aircraft System Integration. So I work on using drones or UAVs, whatever your preferred terminology is, in various science applications and preferentially for operational applications and decision making. So, and one of the things that we do measure with remote sensing, both satellite and drones, is permafrost and degrading permafrost and features which are indicative of degrading permafrost. And I'm not going to talk much about that today. I'm going to talk about some of the basics of permafrost and some of the things that you'll see in and around Fairbanks, and some information that I have found useful over the past few years when I've been traveling around Alaska holding community science night about permafrost with my neighbors. But I don't see my slides.
Yeah, it's going to be up in 1 second.
Okay.
Just how to get it open
Cool.
in the, it wasn't coming up in Adobe. Now it is.
Gotcha.
And I'm going to do that.
Great.
Okay.
So hot.
I'm just making it bigger. Go for it.
Okay, it'll get bigger. So Hot Times in Cold Places is the name of a National Science Foundation grant that we just recently concluded that allowed me to explore permafrost with my neighbors and to come up with ways to communicate this, what can be a complex geophysical phenomena, to folks like my husband, my grandma, stuff like that. So just a quick thank you to NSF for giving us the money to do that over the past few years, and project's done now, but you know, information to share with you. Next slide, please. So what is permafrost? It's ground that has been continuously frozen for at least 2 years. But most permafrost around here has been frozen well longer than 2 years. Think more in the terms of 10,000 to 45,000 years old. It's a mixture of, it's not just ground ice, it's water, it's soil, it's organic matter, it's mammoth hair, it's bug wings, it's sticks, all mixed in and frozen in a matrix in our ground. So as I mentioned, it was, you know, about 10 to 100,000 years ago, and we had most of the permafrost here in Alaska form. Next slide, please. So where is it around the world? So there's just a few little spots high in the Swiss Alps, but other than that, permafrost is around the circumpolar north, and we have the greatest abundance in the United States here, and then of course Russia and Canada. We don't really know what's under the major ice sheets of Greenland. We'll find out pretty soon whether or not there's any permafrost under there. And something that's not necessarily clear in this image is there is actually permafrost that is at the bottom of the ocean as well. So even that crust is frozen. Next slide. So here in Alaska, let's talk about our Alaska. You are all Alaskans also, and you'll be talking to people who have come here to learn about our wonderful state. So permafrost in Alaska is not ubiquitous. And so on the top left, you will see the terms sporadic, discontinuous, and continuous. And those are the different types of ice. Sporadic meaning, and then look under the ground in that image, the brown portion. You can kind of get a feel for the different flavors of ice, ground ice, sporadic, discontinuous, and continuous. So on the far right, on the north slope, totally underlain by permafrost. Very consistent, very deep, lots of ice wedges. Around here, got patches of it. Sometimes you'll hit it, sometimes you won't. Sometimes you'll drive over it, and sometimes you won't. But down by Anchorage, very patchy. There's a few spots, like probably around Campbell Creek Science Center. It's really boggy over there. But you can think of our big mountain ranges as our big division points. So the Alaska Range and the Brooks Range are those divider points. And just on the lower right is just a schematic of what that looks like from a different perspective. Next slide. So on the deeper, more traditional, if you will, permafrost that many folks are a little bit more familiar with from the North Slope or the tundra type environment, this is a graphic of sort of what gives those landscape features life. And it's these ice wedges, what looks like those teeth in the ground. Those are much more pure ice. There is silt that is mixed in with them, but that is very different than what we're building our houses on here in Fairbanks, which is much more of a mixture of silt and water and rocks and ice and organic matter mixed together. These ice wedges are much more water rich, if you will. But they are actually embedded themselves like teeth in a jaw into a more continuous permafrost layer, which you can see the upper portions are labeled with active layer, and then we've got trough and basin. And I don't know if you've walked on the tundra yet, but you know, you've got the wet spot and then you have the high spot. So that's what's represented here with the trough and the basin. But that active layer that runs all along the surface of our Alaska is variable on how much that's going to thaw, but that's what it really means. It's active in that it freezes and thaws every year. It's not permafrost because it thaws out. So, you know, it's where we put our garden. That's, you know, the active layer. It's where you have more biological activity on the permafrost. Next slide. So, folks talk about carbon feedback loops and climate change and permafrost, and without getting too deep into the mechanisms, there's a few ways that permafrost is releasing carbon as it thaws. So the biggest source of carbon that is coming out of formerly frozen permafrost soils is coming from microbes that have consumed the recently released organic matter. So in other words, that ice that had all those bits of old bugs and sticks and mammoth hair is thawing, and now all the microbes are like, yes, carbon. And so they're tuning it all up and spitting it all out as methane and carbon dioxide. So that's a major portion of the carbon that's being released when permafrost thaws. Other sources are geologic sources. So a lot of folks have seen the fires off of the lakes and whatnot that we've lit on fires, researchers have lit on fire, and those are just pockets of methane that are coming out of frozen lakes. And so that's geologic methane. So when you thaw out the permafrost, you remove the lid on the box. And so all that geologic methane is able to get out a lot easier. But there's also a little bit of carbon, actually, little ancient atmosphere in the ice itself. When you look at the ice, you can see these little tiny air bubbles. It's this little tiny ancient atmosphere. It's not a lot of CO2 or methane in those ancient atmosphere bubbles, but there's a tiny little bit. So anyway, and then you can see how that feedback loop works there with the additional greenhouse gases causing increases in surface temperature, additional thawing, more carbon release, vegetation transition, and then all of a sudden you have palm trees in Alaska again. Not yet, but next slide. So this is what I mean about like the parts of permafrost that we build on and live on in interior Alaska. This matrix of ice and water or frozen water and rocks and bits of hair and stuff. So on the left is a core of permafrost. On the right is the same core of permafrost after it has thawed. So as you can see, the water content in the ground is really, really high. And that's why when we have earthquakes, it's like such a wild ride. Next slide. So these are just some really awesome pictures of polygonal ground or patterned ground. That is easier to say than polygonal. But patterned ground like this means you have permafrost-rich place. Next slide. Here's another one that's a little bit greener, also just showing these really huge polygons. So this is from up north. Next slide. Other cool features are pingos. That's where the ice is sort of bubbling up out of the ground. If you've ever seen like a natural spring on the tundra, or this is much more like typical frost heave type feature, but on a massive scale. Pingos are their own little beast in the permafrost world, and there's a couple of them around Fairbanks, but you'll probably see more of the damage to the road. Next slide. So here we are, Fairbanks, woohoo, discontinuous permafrost. So this is all familiar. Here we are. Next slide. And this is what it looks like under the ground. So don't take this as a too elemental model because it is incredibly awesome in its graphic capacity. So imagine this as one of the hillsides in Fairbanks. So on the left side, you have the fuzzy green birch trees and aspen trees. So that's your south-facing slope. That's your high-end property. And then on the right side of that hill, that's the north side. That's where all the black spruce are. And then now let's go inside the hill for a minute. On the north side, you can see all those little blue flakes. That it was representing the permafrost, the frozen ground. So it's on sloped ground, it's on flat ground. It can do that. But over here on the south side where the birch and aspen trees are, the sun, see the sun shining on big orange, sun is shining, sun is melting the permafrost and is allowing those aspen trees and those birch trees with those deeper taproots to really gain hold where they can't do that on the cold soil on the north side. They don't like their feet to be cold. So this is why our hillsides look the way they do. It's because the permafrost is thawed underneath. Next slide. Oh, and then so wild stuff can happen when you have permafrost thaw quick. So some folks may have already seen the Dalton Highway landslide. That's the image on the left. So what happened was some of the permafrost thawed and the whole top layer just slid down off the mountain. I'm pretty sure this has gotten a lot bigger by now. I took this image in 2017 maybe. The image on the right is the same phenomenon just on the coast. So as you can see, as soon as that ice goes, you have the potential for massive, massive collapse. And there's been some crazy images from Siberia with these huge sinkholes, but I have such a hard time wrapping my head around them. I have to keep focus on our interior Alaska. Next slide. So those ice wedges I was talking about earlier, the teeth in the socket of the North Slope permafrost, we have some of those here. And the image on the left is actually in the new permafrost tunnel that's just up the road by Fox. And so that gentleman is 6 feet tall, and that ice wedge, it was revealed, only 9 feet of it was revealed. But that is very, very beautiful, clean, textbook ice wedge. To the right, you can see a cliff. That's what it looks like, same type of ice wedge if you were to just slice away the hillside. Now you see this a lot along the Yukon River and in some other locations across Alaska and Siberia. But those are the same ice wedges that we're looking at in that tunnel image on the left. And down at the bottom, the student that's looking through the magnifying glass, she's looking at a piece of that wedge ice. So it's much cleaner, even though you still have sediment in there, but there's much higher water content, and it still has the smell. It's still, permafrost has a very distinctive organic matter decomposition smell. It's easy for folks to remember the smell of permafrost. If you're able to expose them to a place around town that has melting permafrost. It's a smell they will never forget. On Miller Hill, when you are coming off of Sheep Creek, they just did a whole bunch of bike path improvements about 2 years ago. So if you are leaving the university and you take a right up Miller Hill and you start driving with all the windows down, you'll smell it. And yeah, you'll know it from then on out. Next slide. And I'm gonna just blow through this one. More pretty pictures. Next slide. This is some of what you can see when permafrost starts to thaw. The image on the left is actually here in Fairbanks, a place that all of us actually know, and I'm not going to tell about, but I'm going over. So next slide. Some of the permafrost impacts on roads, they've been super bad this year. I anticipate they'll be awful in another month with all of this thaw. Next slide. And classic coastal erosion. So the problem with coastal erosion, here's the deal. So sea ice protects our coastlines. And when the sea ice is not firm against those coastlines, winter storms will directly hit the coast. When the water directly hits the coast, it melts the ice really fast. And so that's why these winter storms are such a major impact when we have a lack of sea ice, and they're taking out people's houses. So this is 2004. Next slide. And this is a year later. So yeah, it's a major impact in Alaska. Next slide. Just a shout out to the ancient animals of our interior Alaska. These animals lived here about most recently 10,000 years ago, and they are the most dominant types of bones that we find in the permafrost. Next slide. So on the left is a bison. Actually, all of these images are of bison bones that are frozen in the soil. Mammoth and bison are by far the greatest number of fossils that we find. Saber-toothed cats are also found, and horses. Next slide. The micro lenses that create the continuous permafrost that we build on look like this if you were to blow them up. So it's just like these tiny little pancakes of ice stacked on top of each other, fused with little tiny bits of silt. And then we build a house. Next slide. And here's our project team and our website if you wanted to learn a little bit more, and my email address. So I'm not sure if we have time for questions. All of these are going a little bit long, and I apologize, but thank you for this opportunity, and I hope that you learned something about permafrost today.
Thanks, Jess. I do have a couple of questions people put in, and they're both quick ones to answer, I think. So I will pose those first. First question was just where that landslide photo was on the Dalton. The question is it near the YRC, which I assume means the Yukon River crossing?
It's before the Yukon River crossing. It's when you leave Fairbanks, it's on the right. I don't know how far up. It's been a while. It's at least an hour up the highway on the right. But it's before the bridge.
Okay. And second question was just wondering about public access to the permafrost tunnel. I know it's open sometimes, but I don't know if you happen to know if it's a regular opening or how you would go about visiting there.
Yeah, so typically the way you would access the tunnel is you would contact either the university, somebody like me, or you would contact the Army Corps of Engineers. They're the people who officially manage the tunnel. And so going through either us or through the Corps, you can get permission to go through the tunnel in groups of 10, and you can do like 10, 20, whatever, how many people you want to take with you, but about 10 people at a time, 15 people at a time. And so those contacting the Vice Chancellor of Research Office at the university or the Army Corps of Engineers on Fort Wainwright are the way to go with that. However, all bets are off for now. I don't think that they're letting anybody into the facility this minute. Yeah, but it's not open, and it's not something that people who are paying, there are really weird rules about people who are paying to go on trips getting into the permafrost tunnel because it's a government resource. So you'll have to talk to the Corps about those rules.
Okay, thanks. That's all for the submitted questions, Tara.
Okay, I actually have a quick question, Jess, about ice wedges. Where do ice wedges typically tend to form?
Well, we're not making any more. So we're done making fresh permafrost. We just make permafrost go away now. It's indicative of more colder areas. So definitely further up north, but we have a bunch around Fairbanks. So I'm not comfortable to say like where they particularly form, but I know that all across Fairbanks, you can see they run in lines. And so once you find like a small little dip or a sinkhole, you can see a whole line of them because of that polygonal ground shape. All those polygons are under our whole forest here in interior. It's just that we've got great big trees on top of them, so you can't see. But I can't tell you for sure, other than the colder spots have more ice wedges. And because we don't have nearly as many here in the discontinuous zone as they do up north at the Brooks Range.
Great, thank you. All right, well, it looks like that's all the questions we have for now. So we will go on to our next presentation. And the next presentation is from Dr. Todd Brinkman. But like I said earlier, he's unable to be here in person, but he has pre-recorded his presentation. So I'm gonna start sharing that now. I'm sorry for the delay. It always takes me a second to get to it. Okay. And we're going to start.
Hello, everybody. My name is Todd Brinkman. I've been conducting wildlife research, mostly on large mammals, all over Alaska for the last 17 years. I teach 2 courses, wildlife management and a human dimensions of wildlife course, which focuses on human-wildlife interactions. I'm sorry I was unable to be present today. I needed to retrieve a broke down research boat way down the Tanana River, and today was the only day that my colleagues could help me do it. My short presentation will provide an overview of wildlife in Alaska with an emphasis on the interior and Arctic regions. Please feel free to email or call me with questions. My contact info is on the slide. I'm happy to provide more details. Let me give you a roadmap for today's presentation. My brief summary will address 3 main questions. What wildlife do we have in Alaska? What is interesting about Alaska's wildlife, and how are wildlife populations and people's interactions with wildlife changing? I'll do my best to keep in mind that many of the folks that you're guiding may not be familiar with our unique state and all the animals that call it home. With regards to wildlife, Alaska is very unique and different compared to the other 49 states in the US. We have many wildlife species that other states do not. And for the wildlife species that also occupy other states, we simply have more. Alaska is the only state in the US with wild polar bears, Dall sheep, Sitka black-tailed deer, musk oxen, and wood bison. We have the vast majority of the nation's moose, caribou, brown bear, mountain goats, and wolves. In interior and Arctic Alaska, we have some of the largest and most species-rich breeding grounds for shorebirds and migratory waterfowl. We also have black bear throughout much of the state, except for north of the Brooks Mountain Range, small elk populations in coastal areas, and the occasional mountain lion has been spotted in southeast Alaska. Wildlife are bigger too. While other states have moose, The subspecies in Alaska is the biggest. The scientific name is Alces gigas. Gigas is Latin for giant. The males are larger than the females and can reach 1,600 pounds. Our big coastal brown bears can reach 1,500 pounds. Although the grizzly bears that you might see in the interior and Arctic are a bit smaller, averaging around 500 pounds. They're generally quite a bit smaller because they don't have access to the plentiful salmon runs found in coastal areas. The largest polar bears can reach 1,700 pounds. However, the biggest land mammal in Alaska is the wood bison. Reintroduced into the wild in 2015, wood bison can exceed 2,000 pounds, which is a few hundred pounds heavier than their close cousin, the plains bison. As you drive around on the road system, you're most likely to see moose and bear in the interior. On the Dalton Highway heading north above the Brooks Range, it is highly likely that you'll see caribou and musk oxen. In steep mountain areas with rugged, rocky terrain, Dall sheep will be hanging out in areas predators cannot easily reach them. I would not get your clients' hopes up on wolves or wolverines. These are very elusive predators that don't spend too much time in areas with human activity. The best time to see animals is early in the morning or late in the evening. With the long days, this is very early or very late. Those times are also best for people looking for birds. With regards to habitat, river areas and wetlands are good places to focus attention, especially on warm days. Mammals built for cold Alaska climates become heat stressed in temperatures as low as 50 degrees Fahrenheit. Late May and early June is also peak calving for moose, and bear cubs will be following their mothers around. A healthy moose cow will have 2 calves, while moose in very high densities with limited nutrition will generally have a single. Bears have 2 to 3 cubs. Caribou typically have 1 calf, and twins are rare. While people are naturally drawn to young wildlife, please remember that wildlife mothers with offspring.
Oh, sorry. Shoot. I apologize, everybody. That was my bad. I'm trying to get back here.
They're young. With regards to bear reproduction, many folks don't know that denning ecology is different between grizzly and polar bear. Both male and female grizzly bears build dens and hibernate each winter, but only pregnant female polar bears will go into a den. Grizzlies generally excavate the dirt and build dens in the earth, while polar bears generally den in snowdrifts and do not excavate the soil. Grizzlies are built for digging. The hump on their back and the shape of their claws are designed to give them the strength and tools to move rocks and ground with ease. Because of their digging excellence, ground squirrels are a big part of the grizzly bear's diet. The good news is that most of Alaska's wildlife populations are doing really well. Nearly all of our populations are strong. There are somewhere around 200,000 moose, 750,000 caribou, 10,000 wolves, and an unknown but healthy population of black and brown bear. It is natural for many of the wildlife population sizes to fluctuate widely as habitat conditions change. For example, some of the caribou herds on the north slope of Alaska have fluctuated between 100 and 500,000 animals over the last 30 years. The map on the right shows 31 different caribou herds in Alaska. Members of each of these herds generally bunch up in early summer during calving and spread out over a vast area during the rest of the year. Herd number 21 on the map is the porcupine caribou herd. This herd has been controversial because it calves in an area in the Arctic Wildlife Refuge. This area was just opened up to oil and gas development. This herd is thought to have one of the longest migrations of any terrestrial mammal species in the world, with round-trip distances between summer and winter ranges exceeding 750 miles. One notable exception with regards to conservation is the polar bear. The Alaska population is thought to be around 4,000 individuals. This species was listed as threatened in 2008 under the Endangered Species Act. Interestingly, It was listed as threatened not because of an evident or steep decline in the population, but because of a steep decline in critical habitat. Sea ice has been declining rapidly over the last couple decades. And this sea ice serves as critical habitat for polar bear when they're hunting ice seals and when they're denning. With declining sea ice, polar bear are thought to be spending more time on land. This may lead to more human-bear encounters, which is usually not good for the bears. However, it has resulted in a boom in polar bear tourism. For example, the small north slope of Alaska community of Kaktovik now has high densities of polar bears each September, when the sea ice is at its minimum. While conducting research near Kaktovik last year, we observed around 50 polar bear resting on the land waiting for the sea ice to return. The picture on the right is a polar bear feeding on a bowhead whale carcass that was recently harvested by village whalers. I don't feel I should talk about Alaska's wildlife without talking about the importance of wildlife to Alaskans. Hunting, fishing, trapping, and gathering is part of Alaska's culture and people's identity. Hunting and wildlife watching is also critical to the economy, generating billions in spending and activity each year. Somewhere around 125,000, or 1 out of every 6 Alaskans, participates in hunting. Most of the surveys that we have conducted on hunters suggest that Alaskans mainly hunt for the highly nutritious and naturally renewable meat. This is particularly true in rural and remote parts of the state. The figure on this slide shows the pounds of wild foods harvested per person in different parts of Alaska. As you can see, as you get away from urban areas and off the road system, the reliance on wild foods skyrockets. There are many reasons for this. In remote and rural Alaska communities, subsistence is a way of life and critical to the physical and mental health of the residents. Also, commercial foods are limited and very expensive, and generally less nutritious as compared to wild foods. As you can see, interior and Arctic communities harvest over 300 pounds per person to feed their family and share with other households. So what does the future hold for wildlife and the next generation of people who want to embrace and experience the cold and adventurous North? Well, we know that the Arctic is warming at 2 to 3 times the rate that the rest of the planet is. So far, the wildlife seem fairly resilient to these rapid changes in our climate. Probably the biggest concern to Alaska's wildlife is other wildlife species that are not here that are now moving north as the climate becomes more hospitable. New wildlife may carry new parasites and diseases that Alaska's wildlife have not evolved with. There's an extensive surveillance program in place in Alaska monitoring new diseases, bacteria, and parasites that were very uncommon decades ago. For instance, a mule deer, which is a non-native to Alaska, was hit by a vehicle east of Fairbanks in 2017. Studies in the Yukon Territory of Canada found that 50% of the mule deer examined contained moose winter tick. This parasite has devastated moose populations in parts of the lower 48. So far, Alaska hasn't seen any problems, but things are changing fast. So I'll end there. I want to thank you for your time and let me know if you have any questions. I hope you all have a great summer.
Well, thanks to Todd. It's a bummer he couldn't be here, but he did put a pretty great presentation together. And as he said at the beginning, he shared his contact information. So if anybody has any questions for Todd, feel free to contact him. And with that, we will go on to the next presentation. And so Alison is our next presenter. Let me start sharing your presentation now.
Okay. Thanks, Tara, and thanks everybody for joining today. I'll start talking about myself a little bit while the slides come up. I'm the coordinator for a unit here at UAF and the International Arctic Research Center called the Alaska Fire Science Consortium. And we work directly with Alaska's interagency fire management community to help them get the best available science to support their decision making. Next slide, please. So Here's the outline of today's presentation. I'll talk a little bit about background of sort of the natural history of wildfire in Alaska, something about trends with climate change, a little bit about how wildfire management works in the state, and provide you with some information sources and answer your questions at the end. But feel free to put your questions in the chat as I go along, because that makes it easy to remember what you wanted to ask at the end. Next slide, please. So I want to start by stressing, next slide, Tara, thanks. Stressing that wildland fire is a natural part of the ecosystem in much of Alaska. Here's a map of where fires have burned in Alaska since 1940. So the majority of acres burned are in the boreal forest between the Alaska Range and the Brooks Range. And those are ignited mostly by lightning. You'll see fewer acres burned in tundra areas, but there are notable fire histories in the Noatak, on the Seward Peninsula, and a little bit on the North Slope. So you see that big yellow blob up here. That's the Anaktuvik River fire of 2007, the largest recorded tundra fire in history. You also see quite a bit of fire out in the southwestern Alaska. One of the things that's quite different about fire in Alaska versus the lower 48 is the ignition source. So in the lower 48, most ignitions come from humans. Where here in Alaska, we have about, on average, about half of our fires are ignited by humans and about half by lightning. Human fires tend to be, surprise, surprise, where people are. So they get suppressed quickly and they're very limited in their acreage, while lightning fires in Alaska are generally more remote, and fire is allowed to play its natural ecological role. Fires are more monitored and they tend to get fairly large. Next slide, please. So here's another thing that's different about fire in Alaska. Most Alaska's fires burn in a green landscape. Part of this is due to black spruce, which is a fire-adapted species. And of course, it's an evergreen, it stays green all summer. It burns easily, black spruce burns easily. It's structured to carry fire. So it has those branches that come down, those dead branches that come down into the surface that are structured to carry fire up into the tree. And its cones are stimulated to produce seeds and open after fire. And also I wanted to point out to Rick's slide where he showed how much of the year's precipitation comes in the summer. So even we're getting fires even on a landscape that gets a fair amount of rain in the summer, right? There's also another key fuel that you need to know about to understand fire in Alaska. So can I have the next slide, please? And that key fuel is something called duff. So that's the accumulated moss on the forest floor. These photos show duff plugs that have been dug out of the spongy, mossy forest floor that you're all familiar with when you venture out into the woods here. Because the ground is so cold here, these layers of dead moss accumulate year after year without a lot of decomposition, and they dry out remarkably quickly in hot, dry weather, and they carry fire very well, and they can burn very deep for a long time. And the dryness of these fuels, even though they're green on the top, is actually what fire managers are estimating when they tell us that fire danger is high in a specific area. And then I also want to point out, you may have heard about holdover or overwintering fires in Alaska. These are fires that smolder in these deep duff fuels under the snow over winter and then emerge in the spring. And we saw some of these emerge this spring on the Deshka Landing fire of 2019, near Willow this year. Next slide, please. So now I'm going to talk a little bit about a couple of the recent extreme years so that you can get a sense of sort of the scope, what's possible in Alaska fire, because the sky is kind of the limit. So here's a map of the record lightning event that we experienced in 2015 over 3 days around solstice. This is 46,000 lightning strikes over a slightly more than 3-day period. They ignited more than 300 fires, led to the second largest fire season ever recorded in Alaska. That was 5.1 million acres. Next slide, please. And this is a satellite image taken just after that event. Every yellow dot on the image, of course, this is not from the satellite, that was added afterwards. Those are a fire of at least 5 acres that were ignited by that lightning strike event. And you can see the resulting widespread smoke all across the state, which you probably remember if you were here. And yes, you need to know that wildland fire smoke is quite bad for your health. All the evidence, the accumulating evidence just reinforces that it's very, very bad for you. And it's also quite difficult to mitigate with anything like a mask or anything like that. So for vulnerable populations, the elderly, people with asthma, things like that, getting out of the area is probably the best approach if you have problems with smoke. Can I have the next slide, please? And now I'm going to move on a little bit to the evidence of climate change affecting wildland fire in Alaska. I'm really happy that Rick started off this session so I don't have to talk about the evidence that we already have for climate change in Alaska. So I'm just going to talk about fire. Here's the data for acres burned in Alaska since 1950. Then you'll see that the seasons over 1 million acres are called out in orange. And there's a lot of variability in this record, so it's a little difficult to say for sure, but in general, we say the frequency of seasons over 1 million acres has increased by about 50% since 1990, that's the blue arrow, compared to the previous period. In the really big years that we have in Alaska, including 2019, Alaska accounts for more than half of the acres burned in the entire US. And I want to point out that this figure comes from a little booklet that was put out by IARC called Alaska's Changing Environment. Rick contributed a lot of material to this booklet. It's a UAF publication about climate change that's designed for the general public, and you might find that really useful in your work. It's easily accessible online. There's the link, and it has a lot of great information in it. So I recommend that very much. Next slide, please. Okay, so the basic question that people are going to ask you, I think, is climate change changing where and when fires burn in Alaska? In answer to this question, if I were talking to a visitor to Alaska, I would unequivocally say yes. And I'll give you some of the evidence for that. The first is that researchers at UAF and the fire agencies, some of them affiliated with the EPSCoR project, that organized this webinar series, worked together to show that the recent extreme seasons of 2015 and 2019 are directly attributable to the effects of climate change. And I think most fire managers here would agree with that conclusion. In their own work after the record seasons of 2004 and 2005, Alaska changed the statutory start date of fire season in 2006 from May 1st to April 1st. So now we have to have burn permits starting April 1st, and most of the fire management community has to be ready to respond to fires by early April. In 2019, they also extended the end of statutory fire season by a month due to the extreme hot, dry, windy event that we experienced in South Central Alaska that caused the McKinley fire and several other fires and blew up the Swan Lake fire. I think most of you remember that event. And while we're talking about the McKinley fire, I want you to take a look at a couple of aspects of that fire that tell you that something unusual is going on. So the first is the start date. That fire started on August 17th, right? That should, all of you guys are Alaskans, it's after fair time, right? We should have had deep rains, wetting rains that had been going on for several weeks by August 17th. We should not have had a rapid extreme fire event. And I also want you to take a look at the fuels in this photo. Do you see a lot of black spruce? These trees in this photo are mostly aspen and other deciduous trees, which normally we think of as being fire resistant. So an incident like this makes us rethink a lot of the assumptions that we operate under. Can I have the next slide, please? So I'm going to shift and talk a little bit about how people manage fires in this environment. So the first place to start when thinking about fire management is, of course, and you already know this, that in Alaska we have more public land than any other state in the Union. And at the same time, about 80% of Alaskans live in what's called the wildland urban interface.
And right in there.
I know.
So their homes and properties are potentially vulnerable to wildland fire. So there's kind of a disconnect here. Many public land managers want to be able to use the natural wildland fire for resource benefit, which reduces future fire danger and enhances wildlife habitat, among other objectives. But we also need to be able to provide fire protection in this very large area with objectives of allowing fire to play its natural role in the ecosystem while we protect human life and property. So in the next slide, we'll talk a little bit about how that works. So I'm going to start with how we actually protect land from fire. So this slide shows the areas of responsibility of what are called the 3 protecting agencies. So there are basically 3 firemen for the entire state. The first is the Bureau of Land Management Alaska Fire Service. That their area of responsibility is shown in yellow. So they protect 194 million acres, mostly north of the Alaska Range, and also the military areas around Fairbanks. And most of that area is roadless, and so it is their approach to fire suppression is very heavily based in aviation. So Alaska Fire Service is where the smoke jumpers are headquartered. Then in blue, you see the protecting area for the State of Alaska Division of Forestry. They protect 150 million acres. Most of that is on the road system. So those are the human starts, the ones that tend to be problematic and that threaten human values. So their suppression systems are much more based on being able to have road access. And then the third player in the protecting agencies is the U.S. Forest Service, which is shown in green. The Forest Service is responsible for protecting their own lands in Alaska. That's the Chugach and Tongass National Forests. So at the same time, these are the protecting agencies, but they work together with the land management agencies and landowners to determine objectives for any specific area on the landscape for fire management and fire protection. So can we have the next slide? Okay, and that results in this map, which I think probably many of you have seen. But basically, every inch of the state is divided up into one of 4 fire management options. And those management options are for initial response. That's what are you going to do? What are you, the fire manager, going to do in the first 24 hours after a fire is detected at that location? And these management options range from critical, that's the red areas right around places where people live, where those are the first priorities for immediate and aggressive suppression, and then through full, which is sort of a medium, to limited, which is the green. And you'll see that the vast majority of the state is in limited fire management options. That's because it's remote, it's often public land where fire is managed for resource benefit. So that's the approach that the fire management community takes to making decisions. Those are, like I said, those are the priorities for initial response in the first 24 hours. And of course, those responses may change as incidents evolve, as managers become aware of resources that are at risk. But firefighter and public safety are always the highest priority in decision making. And I think we're up to my last slide. So I just want to share with you a couple of information resources that you might find useful this upcoming summer if we have an exciting fire season and you have clients who want to know about what's going on. The best information source for an active fire incident or just general information actually is the Alaska Wildland Fire Information System, and the link is at akfireinfo.com. That's where the fire management agencies post all of their publicly available information. There's lots of great photos. That's where evacuation orders are posted, all that kind of stuff. Everything is all there in a one-stop shop, and I look at it multiple times a day, every day. Then there's also information at the Alaska Interagency Coordination Center. That tends to be information about weather. It's a little bit more for the managers themselves, but there's still some great information there. And then our website, the Alaska Fire Science Consortium, we're really here to serve fire managers. So a lot of our material is for fire managers, but we welcome the general public. And I realized when I was putting together this talk that I forgot to include a great resource that if you're interested in this topic, you should visit. Randy Jant, the fire ecologist who works with us, gave a great talk last February. I'm going to put the link to her talk in the chat, and everybody can have that. And I recommend that if you want to go into more detail about the effects of wildland fire in Alaska. But I think I've got a few minutes for questions, and thanks for your attention. Let me grab that.
Thanks, Alison. Tom, do we have any questions come up?
We have one. It's very interestingly specific. Just out of curiosity, who manages fire response in Little Diomede?
You know, I have no idea, but I can see what I can find out, and I can get back to you. Here comes the link to that talk by Randy about fire in Alaska. You know, I don't know who manages Little Diomede. I would assume that's maybe tribal lands, but I don't know. I'll see what I can find out.
Any other questions for Alison? Not seeing any right away. So thank you so much, Alison. That was a great presentation, and we really appreciate being a part of this.
Yeah, no problem. Thanks for inviting me.
Okay, so we will move on to our final presentation. So Mark, that's you, and I'm going to go ahead and start screen sharing and get your presentation up.
Okay, is it actually possible for me to share the screen so I can use my own cursor? Is that something I can do?
Do you want to try? I mean, you can try.
I just hit the share screen. So what happens if I press this button? Do you see my presentation now?
It says you're screen sharing. I don't see anything yet.
Yep. Okay, let me just try this. Make that full screen. Okay, do you see it now as a full screen presentation?
Just give it 1 second. I think it's just a second. There's a little bit of a delay.
Let's see. If I go to here. Yeah, I mean, is that?
It's not.
What do you see now?
I see your presentation, but it's got the sides still.
All right. Why don't you share the screen? Because I thought I had.
Now it's full screen.
Oh, it's full screen. Okay.
All right.
Use my cursor.
Yes.
Okay. Well, maybe I'll get started. My name is Mark Conde. I'm a professor of physics at the University of Alaska, and I also have a part-time or a half-time appointment at the Geophysical Institute. I study Earth's upper atmosphere at altitudes above 100 kilometers, which is where the aurora occurs. I'm mostly interested in how the aurora perturbs weather in the upper atmosphere. So I don't study the aurora as a phenomenon in its own right, but I study it as a consequence, or I study the consequences of it. Anyway, so this title slide is a slide that I took in Norway in, I think, 2018 as we're waiting to launch a rocket, and it shows a nice aurora over the Greenland Sea, north from Norway there. I think I've just discovered the problem with me trying to share my screen. Oh no, I can advance the slides. So just before we get started, the second slide is a picture that I took from Poker Flat, from our observatory there, as we're waiting to launch a rocket, and again showing aurora over Poker Flat. So this is the sort of aurora you would see over Alaska. All right, I assume my slides are updating as I do this for everyone. So slide number 3 here is just a rough cartoon showing the idea of how the aurora works. So on the left we have the sun. Between the sun and the earth we have what's called the solar wind, material emitted ejected by the sun continuously as a stream of material flowing out through the solar system. When it reaches Earth, it's deflected by Earth's magnetic field. And this cartoon is greatly oversimplifies the story, but basically what you see is plasma getting deflected by the magnetic field and then being funneled by the magnetic field down to high latitude areas near the surface of the Earth. So when the plasma strikes the Earth's upper atmosphere at high latitudes, that impact produces the visible aurora. So that's a sort of a cartoon level. I'll say a little bit more about it in a minute. Really, actually, I'll go back to the previous slide here. What's actually incorrect about this presentation is it shows the material being funneled more or less directly down to high latitudes. That's not what actually happens in practice. What happens is the material accumulates in the region behind the Earth. I hope you can see my cursor here, but in this sort of downstream region in the tail, there's an area called the plasma sheet, and the material from the sun and also some material that leaks up from the Earth collects behind the Earth in this plasma sheet region and then leaks back down to ground level from there. And it's that plasma sheet material following Earth's magnetic field lines down to the altitude of the atmosphere where they strike the atmosphere. That's what produces the aurora. And so the aurora is the visible manifestation of these particles hitting the upper atmosphere. And there's, on this slide number 4 here at the top, you see a picture of the aurora taken from the space shuttle. You can see the limb of the Earth here. There's an air glow layer above that and then auroral arcs standing above that. And then the picture on the lower left is just a ground-based photo of the aurora. So a question that almost certainly Alaska tour guides would get asked is, why does the aurora occur over Alaska? Now, I said that the material that comes from the sun is sort of funneled down to the ground by the Earth's magnetic field. So if the picture on the left, if you look at that, that's a picture of the Earth with a sort of a magnetic field that looks like that of a bar magnet in there. And if you look at where the magnetic field lines go, the ones that sort of leave the surface of the Earth at high latitudes will head quite far out into space. The ones that leave the Earth at low latitudes are confined to remain close to Earth. So at the very simplest level, if you want to have magnetic field lines that go far enough out into space to map to regions where the auroral particles can come from, you sort of have to go to high latitudes. But that's an oversimplification. So if you go to the picture on the right, which is a little bit zoomed out from the one on the left, you can see that the magnetic field of the Earth is actually reshaped by the solar wind blowing past it. And it's no longer looks like a symmetric dipole field. It's got this long tail. It sort of blows back behind the Earth, and at the end, the structure ends up looking like a comet. Now, the problem that you have is if you follow the magnetic field lines that leave the Earth at very high latitudes, if you follow them out into space, they certainly go far out into space, but they don't go to places where there's any real source of material to produce the aurora. If you look at field lines that leave the Earth at low latitudes, they don't go particularly far out into space, but they go some ways out, and there's plenty of material there. But the problem with the field lines at low latitudes is the material that would follow the field line down to the Earth ends up bouncing back and forth and can never penetrate all the way down to the atmosphere. And so in this picture on the right, there's a sort of a yellow region, which is the Goldilocks zone between the low latitudes where there's plenty of material, but it can't get down to ground level, and high latitudes where the field lines, the plasma that is on those field lines can get down to ground level, but there's no plasma. In that Goldilocks zone, that yellow region in the middle, that's where the aurora can occur. And if you actually look at the shape of it, it produces two sort of funnels that come down and strike the Earth at sort of 65 degrees latitude, roughly, something like that. So not too far north and certainly not too far south. So that's broadly why Alaska is a hotspot for the aurora. The previous picture was just a sort of a slice through the noon to midnight plane. If you actually look down on the Earth and map it all the way around in local time, instantaneously what you see is the aurora forms this oval-shaped region. And the one on the left is an image taken by a spacecraft called Dynamic Explorer 2 in the 1980s. And this was one of the first times when we would have a spacecraft that could look down on the Earth and see the whole auroral structure at one time. And you could see this auroral oval there from this DE2 image. The one on the right is the plot that I made using a much more modern spacecraft called Timed. And again, you can see the auroral oval passing conspicuously over Alaska here. You can also see from this picture on the right that Alaska is the only US area that is under the auroral zone. So if you want to be in the United States and you want to see the aurora, you have to come to Alaska. You can see how the auroral oval sits over the surface of the Earth. So this, I'll just go back here. This auroral oval is, you know, what I've shown here is a sort of an instantaneous picture of where the auroral is occurring. There's also a statistical notion of where you would expect the aurora to be, and how that depends on how disturbed conditions are. And by disturbed, what I mean is, you know, how much material is coming from the sun, how much is leaking into the magnetosphere, just how much the sun is disturbing the environment around the Earth. So if on the far left of this picture here, you look at what the auroral oval would look like under quiet conditions, it's shrunken, it's narrow, and you know, it doesn't extend very far equatorward. As you move across the picture here, as activity increases, the auroral oval extends further and further equatorward and gets thicker and thicker, and so the region where the aurora is seen becomes progressively more larger areas and progressively further southward. And in the most extreme conditions, you know, you can see aurora as far south as California or something like that. Here in Alaska, we see aurora even if conditions are not very disturbed. That brings me to the next slide. I haven't mentioned this yet, but the sun is the ultimate source of the aurora. The sun has a cycle of activity. Sometimes it's active, sometimes it's quiet. That cycle has, it's about an 11-year period, or roughly a decade. And so the figure I'm showing here is a rather old figure, but it's really quite interesting. It's a statistics of how often visual observers saw the aurora, not from Fairbanks, but from Chicago. And you can see that there's a periodicity into it. There are peaks roughly every 10 years or 11 years. And the reason we're choosing Chicago here is Chicago is a fair way south. And so Chicago won't see it. You'll hardly see aurora at all unless conditions are quite active. So it turns out places, you know, mid-latitudes and low latitudes, the cycle of solar activity strongly affects how likely you are to see aurora if you're in Chicago or Seattle or Portland or something like that. Here in Alaska, this solar cycle dependence is much less pronounced. And so even when the sun is quiet, even when conditions are quiet, we're far enough north that there's usually some aurora over Alaska somewhere. It might be pretty dim, it might be pretty faint, and you might have to wait till 3 o'clock in the morning and go out and let your eyes adapt. But there would not be many nights when there is absolutely no aurora over Alaska. Maybe it's not bright enough to impress your clients. Maybe they wouldn't even be able to perceive it because they're not trained to look for it, but most nights there would be something over Alaska. Now the next figure is something that I think is of great significance for tour guides who are interested in aurora tours, and it's this interesting phenomenon called the Russell-McPherron effect. And what's shown here is a histogram of how often auroras were seen. Again, I'm not sure where, from Tromsø or something like that, but on the x-axis is month of the year from January through to December. And you see there are 2 peaks, and there are 2 peaks at around about equinox. So what that tells you is, and the peaks are roughly twice as high as the valleys in this 2-peak histogram. That tells you that you've got roughly twice the likelihood of seeing the aurora at equinox, i.e. September or March, than you do at solstice. Now, of course, you can't see the aurora at all during the summer solstice here in Alaska because it's not dark, but in midwinter, in December, yes, there is aurora to be seen, but it's less common by a factor of 2 or so than it would be in September or in March. So that seasonal effect, if a very common question we get is, I want to come to Alaska to see the aurora, when should I come? The answer we usually give people is March, because the Russell-McPherron effect gives you a good chance that there will be aurora in March, and the weather is good and it's a pretty time to be in Alaska. So the answer to the question, when should I come and see the aurora in Alaska, is usually March. Another question people often ask is, you know, how high is the aurora? And you'll hear lots of stories of people saying, oh, I saw this tremendous aurora and it was so bright and spectacular and it reached all the way down to the ground. You could see it touch the mountains. Well, the answer is no, it didn't. If you actually measure the height of the aurora, again, this is old data, but it's a nice plot nevertheless. You know, the height of the aurora peaks somewhere between 110 or maybe down to 95 kilometers. So 95 to 110 kilometers, something like that, is where the bottom edge and the brightest part of the aurora is. That tells you that the aurora is a long way away. It's at least 100 kilometers away from you, even if you're looking straight up, and it fills the sky. So what you're looking at is an enormous structure, a structure that's, you know, thousands of kilometers long and extends up in altitude for many hundreds of kilometers. The auroral curtains are physically enormous things. I want to say a little bit about the types of aurora, or the types of aurora you would see during the course of a night. Starting off with diffuse aurora, which is too dim for you to see by eye. We see it with the instruments. You'll see it early in the evening on the instruments. You don't see it by eye. On a typical night here in Fairbanks, if you went out at maybe 9 o'clock in the evening and looked to the north, you'll often see this faint, quiet curtain sitting far to the north, not really moving around very much. That's what we call discrete aurora. There's many additional flavors and complications to it, but just this discrete auroral curtain that sits far to the north and just doesn't do very much. That's a normal thing that you'll see early in the evening. Sometime, if we're lucky, between 11 p.m. and, I don't know, 2 or 3 a.m. in the morning, the aurora may suddenly brighten and you get this phenomenon called a substorm. And the sudden brightening is what's called a breakup. It's that very spectacular phase of the aurora where there are colorful forms, you know, dancing and moving across the sky, very bright, lots of colors, lots of activity. That's what all your aurora clients want to see, and that's what's called an auroral substorm. Now, I don't know how many of you have seen this, but it's one of these phenomena, once you've seen it, it's hard to unsee, and that is after the breakup, after the bright substorm, there's a period of half an hour to maybe an hour and a half where the sky is filled with these sort of messy looking fragmented auroral forms. But if you look really carefully, you can see, and your eyes well dark adapted, you will often see what's called pulsating aurora. You'll see patches of light flashing on and off, you know, with a period of several times a second to maybe several seconds. And when you see this whole sky pulsating back and forth in brightness, it is a very, very spectacular display. It's not bright, but it's so dynamic. You almost have to train your eye to see it. But once you see it, it's one of them. It's at least as spectacular as the substorm itself, even though it's not as bright. So it's worth. This is something you'll see in the early hours of the morning, from maybe 2 a.m. to 6 a.m. And if you happen to be out doing auroral tours, it's worth, and there has been a bright substorm, it's worth looking and really training your eye and seeing if you can see this flashing, pulsating aurora, because it is very spectacular. The theta aurora I won't talk about because it doesn't really apply here. The next slide, I'm going to try and go through this quickly. It's hard to explain the format, but the time is on the x-axis from dusk on the left to dawn on the right. And essentially there's 4 swaths, 4 different colors of aurora, and each line in this is a cut from the north horizon to the south horizon. The reason I'm showing this picture is it gives you a sort of a notional idea of how the aurora might evolve during a well-behaved night that's sort of following the template. Very few nights do. Everything's, you know, no night is exactly the same. No night is exactly textbook. But on a textbook night, something like this would occur where early in the evening on the left side here, you can see some diffuse aurora, which is not very bright. And then up at the very top, if I just look at the top panel, there's a strip running from about 5 UT to about 9 UT, where there's just a little band sitting way up to the north. That's that discrete aurora, those curtains. If you went outside and looked at the sky, you would see an auroral arc sitting low on the horizon far to the north from Fairbanks. And then on this particular night, somewhere around about 9 UT, there was a sudden brightening and the sky was filled with a bright, active aurora, in this case actually for a couple of hours, which is longer than typical. This is probably several auroral substorms that have gone off one after another. And from about 11:30 UT till, well, you know, almost dawn, there's this sort of odd looking stuff in the picture here. This is that pulsating aurora. And as I said, if you can see that, it is really quite spectacular. The storm, which is this bright phase here in the middle of the night there, that's a phenomenon that was really first described comprehensively by Akasofu, and he did it by getting all-sky camera pictures from all around Alaska and Canada and Russia and assembling mosaics together and sort of forming a picture of what was happening on a global scale based on individual observations from individual cameras. There's a classic picture he drew here. I won't go through that, but I will show you the next slide, which shows a spacecraft view of a substorm. And there's a series of pictures, again, I think taken by this Dynamics Explorer 2 spacecraft, showing the Earth from some distance away. And on the top left, you can just see a little brightening in one area there. That's the substorm initially starting. It's like the detonation of the substorm. And if you follow these pictures through, you'll see that the auroral oval has got dramatically brighter, dramatically thicker. And if you're on the ground looking up in places like this third row of images, your whole sky would be filled with bright, active auroral forms that, as I said, these are what your auroral clients would really like to see. A question that's often asked is, do they have the same aurora in the southern hemisphere as we have in the northern hemisphere? And this cartoon that I'm showing you here sort of motivates why you might expect that. You know, if the aurora is caused by charged particles moving along the magnetic field lines, well, a magnetic field line that leaves the Earth here in the northern hemisphere goes out into space, and the same field line strikes the Earth in the southern hemisphere. So something that originated in the middle of that presumably would travel in both directions, and there would be aurora in both hemispheres at the same time, and possibly even similar looking aurora. A lot of work has been done on that, and you can see two all-sky camera pictures here that show not exact mirror images, but auroral forms that are, you know, broadly speaking, the same sort of general structure, showing that, at least in this instance, there was what we call conjugacy. In the northern and southern hemispheres did see the same aurora more or less at the same time. Similar work was done here in Alaska in the late 60s, early 70s with aircraft flying over Alaska. You can see this track here from, you know, interior Alaska down to south of Anchorage there, and a corresponding aircraft flying at the magnetic footprint of the same field lines, which in this case happens to be south of New Zealand. Photos taken from those two aircraft at the same time, and they actually saw essentially mirror image forms. So it doesn't always happen, it's never perfect, but there is, you know, auroral conjugacy is a thing, and generally you would expect the aurora to be similar in both hemispheres. Colors of the aurora, this slide here is a spectrum. The bright line labeled 5577 angstroms, that's the sort of lime green oxygen emission that you would commonly see. There's another emission at 6300 angstroms. Actually, that's a little bit hard for your eye to see. It is seen, but it's a little bit hard for your eye to see. There's a blue emission at 4278, which comes from singly ionized molecular nitrogen. And there's a whole bunch of bands out here in the red from neutral molecular nitrogen. And these ones here matter because during that substorm, you'll see a red fringe along the bottom of the aurora, and that's due to the sort of net sum of all these red features here being lit up. Sometimes people will say they see purple, and that's a combination of this red and this blue, again, usually on the bottom during very, very active aurora. That's all I want to say about color. Not a lot to say there. I want to finish up by saying a little bit about how you would predict the aurora, because from the perspective of a tour guide, that's a question that everybody's going to ask, you know, is there going to be aurora tonight? There's basically three things you can do to predict the aurora. Two of them involve looking at the sun and trying to imagine what the sun is sending towards us. And then the third one involves looking at data from a spacecraft that's about 200 Earth radii, 200 times the radius of the Earth upstream from Earth, between the Earth and the sun. There are several spacecraft that sit there. And at that location, 200 Earth radii upstream, it takes the solar wind about an hour to get from that spacecraft to the Earth. So you get about an hour. If you look at what the spacecraft is seeing there, you get about an hour's warning as to what will strike the Earth there. So looking at the sun, you can get a longer term forecast. Looking at the spacecraft data, you can get a 1 hour forecast. Now, what to look for on the sun, there are basically two things we look for. There are things called coronal holes. I'll show you a picture of that in a minute. It's a region where the atmosphere of the sun essentially has a hole in it, and the sun is leaking material out. These things last for months, and you can predict when they're going to come around again. If there was a coronal hole that occurred a month ago, it takes the sun a month to rotate. So 27 days later, which is the rotation period of the sun, you would expect activity from that same feature. You can actually see it on the spacecraft images. You can see whether the hole still exists this month that was there last month, and you can use that to forecast whether we might get activity. There are also eruptions that occur on the sun. We have to watch for regions that might produce an eruption. When an eruption occurs, if it appears to have ejected material in the direction of the Earth, then we can predict that it will take about 2 or 3 days for that material to reach the Earth, and we would expect there to be aurora in response to that. Spacecraft data, there are several things we look at. We look at the density and speed of the solar wind, but the single most important thing is the direction. There's a magnetic field embedded in the solar wind, and if that magnetic field turns southward, You can watch the magnetic field in real time. If you see the magnetic field turn southward by more than a few nanoteslas, almost certainly the aurora will pick up an hour or so later. It's a very reliable predictor of impending activity. This is a picture of one of these coronal holes. It's taken at far or extreme ultraviolet wavelengths. It's the emissions are coming from the corona of the sun, not from the surface of the sun. This is such a short wavelength that it takes very high temperatures, many hundreds of thousands to millions of kelvins to produce optical emissions at this temperature. The corona of the sun is that hot. The surface of the sun at these wavelengths looks dark and black and cold. It's not hot enough. So we're looking through the atmosphere. What we see is this dark patch here. That's a hole in the atmosphere of the sun that allows the sun to leak material out, and that produces a stream of material that comes from the sun. It's just like a garden sprinkler spinning around. That stream spreads out through the solar system, and if we see it come past this month, next month, if we see that the hole is still present, we can predict that aurora will occur. These images of the sun that you look at, the features move from left to right across the disk, and they have to get to about where this hole is here, a little bit past the middle, a little bit to the right of the center, before the material that is leaving them would hit the Earth. So you can watch this hole appear over the limb of the sun and see it moving across the disk, and you can predict, a week or so ahead of time, if you see the coronal hole there, that when it gets in the right position, there should be aurora. Eruptions are, of course, more sporadic. We can look at the sort of active regions on the sun and predict that there's a region that might produce an eruption, but until it does, we just have to wait. But once the sun produces an eruption, there's a picture here on the right, which is, I think, an example of a solar prominence erupting. That will eject a big cloud of material from the sun, and if we think it is directed towards the Earth, people like Space Weather Prediction Service will provide a diagnosis of the eruption. If it is directed, then 2 or 3 days later, we would expect it to hit the Earth and produce increased auroral activity. So basically, the coronal holes and the eruptions are features on the sun you can use to predict the aurora, possibly weeks and certainly days ahead. And on an individual night, you look at the solar wind speed, the solar wind density, and the interplanetary magnetic field to get a prediction on the timescale of an hour or so ahead, because the spacecraft is about an hour upstream in the solar wind. Just finish by saying that the sun goes through this 11-year cycle of activity. I've mentioned that before. This is a plot going back over many decades showing the peaks and troughs of activity. The plot at the top is a famous thing. It's called a butterfly diagram. You plot where the sunspots appear on the surface of the sun as a function of latitude on the y-axis and time on the x-axis. During the solar cycle, the spots first form at mid-latitudes, and as the solar cycle progresses, they get squeezed towards the equator. And so if you plot where they are, you end up with these butterfly shapes that repeat once every solar cycle. So this 11-year period of activity, right at the moment, this particular plot finishes at 2010, but right at the moment we're in the middle of a minimum, and in the next few years we would expect the activity to pick up again. Now, something that everyone should be aware of is that back in the late 1600s, 1650 to 1700, the solar cycle more or less shut down for about 50 years. It's a very famous thing called the Maunder minimum, and during that period there was hardly any solar activity, and then you can see subsequently the solar cycle restarted and oscillated again. For this slide, if you actually look at the last few solar cycles that we've had, you can see this one is the one that peaked around 1990, this is the one that peaked around 2000, and this is the one that peaked a little after 2010. You can see there's a decreasing trend in these peaks, and this plus multiple other indicators are suggesting that solar activity is declining at the moment. And there's a number of indicators that suggest we might be heading into another one of those Maunder minima, during which the sun would potentially be inactive for decades to come. That, of course, has implications for whether we see the aurora here. It also has implications for climate change, because this solar activity is a small contributor to climate change. When the sun is active, there's a little bit of extra heating. So if the sun shuts down for 50 years, that might mask some of the effects of climate change, because there's less of the solar activity component contributing. So we don't know, but there's this plus many other predictors are suggesting that solar activity is declining, and the aurora might become something you have to, will only be seen in the far north of Alaska in decades to come. All right, so I will finish there with a summary just to say that aurora is caused by plasma that is stored in the tail region of the Earth's magnetic field, leaking and raining down onto Earth's upper atmosphere. It occurs in oval-shaped regions surrounding the north and south polar regions, not at the very highest latitudes, but in these ovals that surround the polar regions. It has an 11-year cycle of activity, which is very significant for aurora at mid-latitudes, a little bit less so for here in Fairbanks or here in Alaska, because Alaska's at high enough latitude that we do see aurora even when the sun is quiet. Even if the sun isn't particularly active or conditions aren't particularly active, the whole magnetosphere can become unstable, and that triggers this substorm event that is common, seen many times a month, and that produces this bright, spectacular Hollywood aurora. We can predict aurora by looking at eruptive events on the sun, looking for coronal holes, and so you can predict the aurora days or even weeks ahead by that method. And if you look at the spacecraft data, you can predict the aurora an hour or so ahead. And that final thought, there's multiple lines of evidence that suggest the sun might be heading into an extended period of quiescence. So auroral activity may be weak by historical standards for the next few decades, perhaps. We don't really know. A couple of links here to things that might be useful if you're in the business of aurora tourism. But with that, I'll stop there.
Thanks, Mark. That was awesome. Do you want to stop sharing your screen?
Oh, if I can figure out how do I do that? Oh, it says stop sharing. A big red button there. There we go. Yep, got it.
Yeah. So, Tom, do we have any questions for Mark?
We do. We have 3 of them, in fact. First one, I have seen what would appear to be small prisms on 3 occasions within the aurora. What causes this?
Well, I'm not sure what the questioner means by small prisms. Do you mean auroral structures that look like prisms? I think that might be an accidental or coincidental alignment of the auroral forms. There is a phenomenon called the corona. I said that the aurora starts at about 100 kilometers roughly, and I didn't really say this, but it extends up to 200 or 300 kilometers in height. It tends to have small folds in it. So if the aurora is directly overhead and you look up, you get this structure that is called the corona, where it almost looks like there are rays bursting out from a point in the sky. And I guess that, that sort of, that gives a triangular sort of structure or shape to it. And maybe that's what the questioner means by prisms. So maybe what they're seeing is the corona feature, where it's just perspective that makes those folds appear to disappear. They look like they're sort of converging on infinity as you're looking up this several 100 kilometer high structure that's directly overhead. So perhaps that's what they're referring to.
So she then went on to describe them as small rainbows?
I would imagine that I'm not sure, but very commonly, if the sky is dark and it's nice, conditions for being outside, there may be ice crystals in the air, and that might be, unrelated to the aurora. I'm unaware of any auroral phenomenon that would produce small rainbows. There's certainly atmospheric phenomena that would do that, but I'm not aware of any auroral phenomenon that would do that.
Okay. Next question. Clumping all of Alaska together as an equal opportunity type aurora viewing destination is disconcerting to those of us in the Fairbanks Coldfoot region. Can you delineate a little bit more within Alaska about where the places are to see the aurora, where the opportunities are for viewing?
So, it's a statistical thing. You can look at the frequency of occurrence of aurora. If you're trying to say where should I go to see the aurora, you have to think of it on a statistical basis. So particularly now, when the sun is quiet, basically the further north you go, the more often you will see aurora for the next several years. So if you were to go to, Yukon Crossing or Coldfoot, or the Arctic Circle or something like that, that actually significantly increases the chance that you will see aurora over what you would see in Fairbanks. And we have instruments that are between Fairbanks and Kaktovik. And instruments up at Kaktovik or Barrow or something will see the aurora every night even on the quietest nights that exist. Here in Fairbanks, you know, most nights you'll still see something, but it's pretty weak, and maybe you wouldn't perceive it by eye. The instruments see it. So now, when conditions are quiet, statistically the aurora will be more contracted. So the further north you go, the better. During solar maximum, I think it doesn't really matter very much. You know, I guess if you went all the way down to Anchorage, you would still see the aurora less frequently than you would see it in Fairbanks, even at solar maximum. But it's not a very strong dependency. It's not like, well, if you go to Delta Junction, you'd have a significantly different chance of seeing the aurora than you would at Fairbanks. It's mostly driven by latitude, and it's not a very strong dependency. But if you went several hundred kilometers north, it would make a significant difference.
Okay. Final question. Aren't most of the auroras that we see in the Fairbanks region caused by solar wind?
Well, in a sense, all of the aurora is caused by solar wind. It's a complex interaction between the solar wind and the Earth's magnetic field. And some of the material that actually ends up raining down on the Earth actually originated from the Earth. There's mechanisms by which Earth actually loses material from its upper atmosphere. It gets trapped in the magnetosphere and, you know, eventually finds its way back down again. But I think a good answer to that question is that essentially all of the aurora is caused by the solar wind, because the electric fields that drive the aurora, most of the material that precipitates down to cause the aurora comes from the solar wind. So I think the answer is yes. I think all of the aurora is really a solar wind phenomenon, whether it be in Fairbanks or anywhere else. I think is a true statement.
Okay, that's it for the online.
Awesome. Well, thank you so much, Mark. And so if there's no other questions, well, I guess we could see, are there any questions out there for any of the speakers that didn't get addressed already? And, you know, if not now, you know, you can feel free to reach out to Explore Fairbanks or Alaska EPSCoR, and we would be happy to help out with that. I'm just seeing something pop up in the chat. Nothing yet. But anyway, I want to thank everybody for joining us today, and especially all of our presenters for sharing all of their presentations with us. They were full of great information, and it's just a really, really exciting event here. It was, I'm excited to be in Fairbanks and learn all this science, and looking forward to having some more tours eventually, and hopefully that'll happen sooner than later. But anyway, I would again thank you, everyone. Scott, do you have anything you want to close out with?
Yeah, well, no, yeah, thanks, EPSCoR, and thank you to all the panelists for a great job, and to our partners on board. We will be sending out the link to today's program. It'll be on the next, send on the partner e-news that you receive. So watch for that. You can share it with your colleagues and other employees you might want to have this, get this valuable information. So thank you all for your time today.
Yep. And I also want to apologize for any hiccups. You know, this is a new format for everybody, and so things are going to happen, and hopefully next year we can go back to doing this in person again. Awesome. All right. Well, thanks everybody.
Take care.
Bye.
Okay, bye.